Come to section 2.3, which is acceleration. So far, we have learned about displacement, and we saw that rate of change of displacement with time is velocity. And now we will see that rate of change of velocity with time is acceleration. So if you remember at the start, for one-dimensional motion, I showed you three quantities that we were interested in defining. They were displacement, velocity, and acceleration. And we want to proceed from there to use these to describe our motion later on. So in this section, we're going to learn about acceleration. And we're going to define acceleration, which is a vector quantity. Okay, so this is a bold letter, vector quantity, or you could have an arrow above it. It's the change in velocity, so delta v over delta t. So change in velocity with respect to time. When you open delta v, it's going to be v final minus v initial. Same way for delta t, t final minus t initial. Okay, so this is the definition of acceleration. And its units, remember velocity is meters per second. Now you're dividing by another unit of time, so meters per second squared, okay, is the SI unit for this. So we just saw that average acceleration is a vector quantity. There are a couple of things that you want to note. So when in one-dimensional motion, again, the direction of the acceleration, we're just going to use a positive or a negative sign. That will be sufficient for us. So if it's a positive sign, then the velocity and the acceleration are in the same direction, and the acceleration is to the right, okay? And when they are in the same direction, the velocity and acceleration, then the speed of the object increases with time, okay? So it doesn't matter whether the velocity and acceleration are both to the right, then the object is speeding up. If your velocity was to the left and your acceleration is also to the left, then both are speeding up in the left direction or negative direction. But when they're in opposite directions, so your velocity is starting off to the right, your acceleration is to the left, so acceleration is negative, so they must have opposite signs, then your object will slow down. So now you're coming to a stop, okay? So negative acceleration just means an acceleration towards the left, and it does not mean that the object is slowing down. Remember, if you have a negative velocity and a negative acceleration, your speed is actually increasing in that negative direction, okay? So it's quite confusing when you use terms like deceleration, okay? Deceleration typically means a decrease in speed. It does not mean a negative acceleration, because a negative acceleration can be associated with an increase in speed. Okay, so it's important to differentiate things. Just like we defined an average velocity and instantaneous velocity, we're going to define the average acceleration and the instantaneous acceleration. So we saw that this part here gives us the average acceleration. And if you take this in the limit delta t tends to 0, then we're going to get our instantaneous acceleration. There's a vector quantity. That means the acceleration at any given instant, okay? And we will find later on that we are interested in describing motions which have uniform acceleration. That means the acceleration does not change with time. If that is the case, then your instantaneous acceleration and your average acceleration are the same, okay? So the average of, say, 5, 5, 5, 5, 5 is 5, yeah? We saw in the past that we obtained instantaneous and average velocities from a position time graph. If you plot a velocity time graph, then you can obtain information about the acceleration. So you can get instantaneous acceleration, which is the tangent at any given point of this velocity time graph. And if you take the slope between any 2 points, that's going to give you the average acceleration between those 2 points in time. So we'll look at some examples. Here's a graph. Remember, I always said look at the axes first when you're given a graph. So this is a velocity time graph. The first word I mentioned, velocity, goes on the y-axis. The second one goes on the horizontal x-axis, so velocity, time. And if this is our path here in the velocity time graph, this red or orange line is the actual change in velocity with time. But if you consider any two specific times, let's say P is our initial time, so Ti, and we take some final position here, Q, okay, so Tf is our final time. Remember for final position, it doesn't mean the object has stopped here. It just means these are the 2 points we're interested in considering, the initial and the final. The object could be moving before the initial, it could be moving after the final, so don't mix these things up. If you go at the initial time to P, you see that the corresponding velocity is this initial velocity Vi. And if you go look at the final time and go to Q, your corresponding velocity on the y-axis is some Vf. Okay, so it's this change in Vf minus Vi, which is this distance here, same as this distance marked here, or rise, yeah, delta V, over run, which is going to be this distance here, yeah, delta T, which is Tf minus Ti. So you can see the slope of this blue line, which joins P and Q, is going to give us delta V over delta T, which is going to be our change in velocity with time, or acceleration, which is average acceleration. Let's say you wanted to know the instantaneous acceleration at P. What would you need to do? You would need to draw a green tangent line here. Of course, it doesn't have to be green, but we have taken this color coding. So if you made a tangent line here, which would touch this curve at just one point in P, it might be on this side, actually, the way it's looking. And the slope of that green line, which is not shown here, would be the instantaneous acceleration at P. Clearly, it has a different slope from the slope of the blue line. Okay. Similarly, if you wanted instantaneous acceleration at Q, here we do see this green line, and its slope is going to give you the instantaneous acceleration at Q. Completely different slope from that of this blue line. Remember, if two lines have the same slope, they're going to be parallel to each other. These two lines are not parallel to each other. In fact, they intersect at Q. Okay. So let's clarify this a little further with some examples. Here we have a car, and we see its velocity vector in red. So when you look at a velocity vector drawn as an arrow, the length of the arrow tells you the magnitude, okay? And the direction of the arrow shows you the direction. So we see here that the velocity length, or the magnitude, is constant with time, yeah? The object is moving to the right, so the velocity is positive, and it has a uniform magnitude. If the velocity is not changing with time, what would be our acceleration? It would be 0. There is no change in velocity. Remember, acceleration is the rate of change of velocity with time. And here we have no change. So just from this one picture, we can deduce that A, the velocity is uniform, B, the velocity is to the right and is positive, C, that the acceleration is 0 and is constant. Let's look at another picture. The same car, but now it's moving differently. So at the top here, we have the red velocity arrows. Below, we have the purple acceleration arrows. Let's look at velocity first. It's constantly to the right, so velocity is going to be positive. What's happening to the velocity vector in length? It's increasing in length, which means we have a positive slope in the velocity time graph, yeah? Which means what for acceleration? It means we're going to have an acceleration. So let's look at this acceleration. And here I would say all these vectors look to be of the same length. So it suggests that we have a uniform acceleration, also to the right, okay? Velocity and acceleration in the same direction. What does that imply for the speed? It implies the speed is increasing to the right, yeah? So this car is speeding up. Yeah? Okay, so we could tell quite a lot of things from this one diagram. Yeah? Let's look at this last diagram. Again, we have the car. It's moving to the right. Okay, here's our velocity vector. What can we say just with the velocity vector? It is slowing down. The magnitude of this arrow is shortening, which means the velocity or the speed is reducing. It might be gradually coming to a stop. Is that consistent with the direction of our acceleration arrow? Yes, it is, because they are in opposite directions. Remember, whenever they are in opposite directions, your object is slowing down. So that is indeed the case, as shown by this arrow here for the velocity vector. And the acceleration is actually uniform. The length of this arrow is not changing. So we have, again, uniform acceleration, but in the opposite direction to the motion. So with uniform acceleration, the car is slowing down. Okay? Here's a problem I'm going to leave you with. You want to think about which position time graph, A, B, or C, is impossible and why. So here we have 3 position time graphs. Let's call the first one A. This is B, that's erased, unfortunately. And this is C. And you need to work out which one is not possible. And you're going to write about this in the discussion board. So I want you to throw up your ideas with your reasoning. So don't just write A or B or C. You need to give us your reasoning. And we'll stop here for this section.